Good afternoon and welcome to the tool demonstration for Rapita. Our demonstration has been given by Dr. Andrew Coombes this morning, who runs the Marketing and Engineering Services Group at Rapita Systems Limited, a company which specialises in tools for on-target verification of high-integrity embedded software. Since 1996, he's been involved in the development and commercialisation of software tools for embedded real-time applications.
Okay, thank you very much, Sarah. Okay, so as Sarah said, I'm Andrew Coombes from Rapita Systems. We specialize in on-target verification tools. Our primary industries are aerospace and automotive. We also do some work with space applications as well. We are a spin-out from the University of York a number of years ago now, and a consequence of that background is that we do participate in a number of research projects. So what I'm going to be talking about today is some of the research that's come out of one particular project we've been working in, particularly called Armorasa, which is to do with the parallelization of software tools. Rapita itself, we have a main product line based around the RVS Rapita Verification Suite line of products, of which there are three main tools available today. RappiTime provides worst-case execution time and detailed timing analysis. RappiCover provides structural code coverage, and RappiTask provides RTOS schedulability and visualization. We also have a number of other activities, products that are in various stages of development, often through the various EU research projects, which we make accessible to our customers through something we call the Early Access Program, where they can get access to our tools in whatever stage of development they happen to be in. Now, I said that Rapita is an on-target verification company. What this means is that we actually measure the behavior of software running on an embedded target and do the analysis. Because we have this idea at the heart of all our tools, we have a kind of a centralized architecture, a centralized verification engine, if you like. So this slide actually illustrates that. So starting with a conventional development process, on the right-hand side of the diagram, you see we start with source code, which then gets pre-processed, compiled, linked, put into an executable, which is then run on a target to generate in response to tests. Now what our toolchain does is, as the code gets compiled, we insert instrumentation into the code. And as we do the instrumentation, we perform a structural analysis on the code that allows us to understand the structure of the code. Then, when the instrumented code gets executed on the target, it produces a set of trace data. The combination of the trace data with the structural analysis allows us to perform all kinds of interesting reports, which we'll be able to go into in a few minutes. One of the challenges of working with embedded systems is, of course, no two embedded systems are the same, and so we need to be very flexible in how we connect to the targets in order to get the trace data off. So what we have here is an illustration of the number of ways in which we could potentially connect to targets to get data. So one possibility is to collect data through an I/O port via our data logger product, the RTBX, or via a logic analyzer, just simply reading constant values and timestamping them as they appear. Another approach is, especially if you have an older architecture, you might have an exposed address bus, which would be possible to connect to in a similar way and timestamp values that appear on that. If you have newer generations of debuggers, so for example Nexus or ETM from ARM systems, it may be possible to trace memory activity that's happening there. Yet another possibility is to actually record verification data into a memory buffer, which is then downloaded via debuggers or possibly offloaded from the network via whichever communication mechanisms could exist. So, for example, a Ethernet card. Yet another approach that exists is if a a reasonably accurate simulator of the target exists, we could use that as a basis for collecting the verification data. So I mentioned earlier we have the early access program. As of today, the three tools that we're going to be talking about that are currently commercialized, RapidCover, RapidTask, RapidTime, are available at version 3.2. The other things that we're going to be talking about, Nappy Check and the use of all four tools on Multicore, are all available via our early access program. So RapidCover is a structural coverage analysis tool. It provides support for a wide range of coverage metrics, including all of the ones that are commonly used by various standards. The two that concerns most of all are DO 178B and C and ISO 26262. So we provide the ability to qualify the tool to those two standards. Because we focus on embedded applications, it's very important that the overhead of instrumentation is extremely small, and so RapidCover offers the smallest on-target footprint of any structural coverage tool. We also provide a number of other features which make reporting coverage easier. So, for example, we have the idea of justifications, which allows you to explain perhaps why a particular piece of code wasn't executed. We also allow report merging. So if you have partial coverage reports from different test cases, it's possible to bring them together into a single test case. Now, the multiple support aspect for RapidCover comes in when you have a piece of code which is replicated across many cores. And in that situation, what you want to do is to record the coverage data on a per core basis and on an aggregate basis. So we actually support both of those situations. We also allow for different coverage profiles per core, if that was also something that was interesting. So it would be possible, for example, to measure statement coverage on one core and MCDC on a second core. This allows for mixed criticality systems. So rather than go into a full demonstration of RapidCover, I've just got a sort of a screenshot here which is illustrating us looking at decision coverage, and we can see that there's an element of the code that hasn't been covered. So we can see that both at the summary level in terms of the grid at the top of the screen, and at the source code level there you see code highlighted to show that it hasn't been executed. And we can see the subsequent report where we've amended our test cases to include that particular situation. RapidTask is a tool which allows us to visualize real-time operating system behavior, event scheduling, so on. It allows you to collect all sorts of different metrics from task runnable level, or even at a slightly deeper level than that. So we can look at things like the CPU utilization, the response time of tasks, and interference between tasks that happen to be running roughly concurrently. Now, of course, the idea for multi-core on an application like this is very clear what you need to be doing. You need to be extending reporting to cover many cores. So what we can do now is actually look at RapidTask in practice. So what we have here is the report that is generated for RVS, which incorporates all of the different reports from RapidCover, RapidTime, RapidTask. The first page that we see is just a summary page showing when the report was generated, any issues that have come up during the generation of the report. We also have other pages that report a static view, so we can see all of the lines of code that have been included in the code that we're analyzing. We can see the number of tests that have been executed on each of the parts of the system. And in the case of RapidTask, we can actually see at this level just a very simple report of the CPU utilization of each of the runnables or tasks in the system. So this is kind of a very top-level view. We also have a visualization view, which allows us to see what's going on in slightly more detail. So there's a number of different ways that the information can be presented. So what I'll do is I'll go for the stack view. So what we're seeing here is the behavior on a per task, a per CPU call basis of each of the tasks and runnables that are going on, with time progressing down the page. So what we can see perhaps is, if we go to a particular block of code, we can zoom in on it and see what's going on in slightly more detail. So what we see here on CPU 1 is there's a function which starts up message dispatcher 2, you can see there, which then calls a subfunction which is dispatch message 2, which then calls check CRC2, returns back to dispatch message, and then it calls finally enqueue message before returning out of the functions. So we can see from this view the kind of the stack depth of the things that are going on, as well as the order in which things are getting called. So that's one part. We can also look at the data that's come out of this in a number of different ways. So for example, we can look at the CPU load, which shows us the CPU load on each of the cores in the system, and it's synchronized so that we can see that at a particular time if there are common patterns running across the different CPUs. Now we might see, for instance, that something of interest occurs. So just here we see that there's a very high CPU utilization on CPU 1, and that is, well, let's dig into that and see what's going on there. So we can see that that's occurred this particular time here. So we zoom out a little bit. That's better, sorry. Okay, so the high CPU utilization on CPU 1 has taken place at this interval. So we can see that message dispatcher starts off, it calls dispatch message, and then there's a sequence of enqueue message, check CRC, running one after the other. So we can see there's a whole bunch of things that are using the CPU. We can also see what's happening in a slightly different way. We can look at the separation from, the periodicity from ready. So what this is showing is the periodicity of each of the runnables in the system. Now obviously this is a rather complex view, so we can simplify it to look at the things that are of interest to us. So if we just look at dispatch message 2, what we see here is the period of dispatch message 2 as it evolves over time. So we see that for a lot of the time it's got a period of 20 milliseconds with an occasional period of 40 milliseconds, which suggests that what's happening is it's missing a core. And then this point where we receive that block of high utilization, high CPU utilization, there's a whole bunch of calls of dispatch message that are coming very close together. So if we just return to this, what we can also see on this diagram is blocking occurring across a number of cores, where on CPU 0 we have this master lock function, and at that time that that's running, each of the other cores are actually forced into an idle state. So we can see the multi-CPU synchronization going on here. Rapitime is the third tool we're looking at, which is performance measurement timing analysis tool. So what Rapitime is mostly about is about finding worst case execution time and allowing us to adjust our tests to be able to improve the analysis so that we can create tests that follow the worst case execution time. So Rapitime is reporting what we call the high watermark, the longest observed execution time, and the worst case path. And the idea is to repeat the process, making the worst case path and the high watermark as close together as possible. It also allows us to see places where in the code where it would be really good to optimize. So there will be pieces of code which allow you to see that there is what we call a very high contribution. That one piece of code contributes a high percentage of the worst case path. Now, from the Palmarasa project, there was a certain amount of theory developed to be able to handle bounded multicore, so it bounded the interference between multicore systems, which is something that's a bit of an open problem with some of the other cores that are commercially available at the moment. So just to give you a little background about what it is that Rapita is doing for determining the worst case execution time. If you imagine you've got this code structure on the left-hand side, when we perform the instrumentation, when RVS does the instrumentation on the code, it builds up this structural model, as I said earlier, and we get this on the right-hand side of the diagram. Now, as you run a test case, you measure the execution time of the code, and we can see there's 2 test cases we run. We've achieved 100% coverage of our code, and we've got these 2 times of 110 microseconds and 85 microseconds. Now, the instrumentation we've collected allows us to see the execution times of each of the blocks of code in the system, and by taking the structural model with the execution code, it's possible to identify that there's a worst case path through the code that we haven't actually executed, 140 microseconds. So what we would do then is we would construct a test case which allows us to follow that path, or possibly that path's infeasible, in which case we could instruct Rapita to say that this is an infeasible path and you need to consider the next worst case path. So to see Rapita in action, we return to our report. So we can see on this tab here the worst case execution time. So right, let's go for the worst case execution time across all of the runnables in the system. So we can see that each of the components within the system has got a particular worst case execution time, and we can actually compare that against the minimum, the maximum, and the average execution times that we've seen through the tests we've done. So we can see there's very little variability in most of the modules, but with message dispatcher there is some variability between the maximum observed, the high watermark, and the worst case execution time. So it would be interesting to identify exactly what the cause of that variability is, and ideally to update our tests to minimize that. So we can dig into message dispatcher, and what we see here is if we look at maximum execution time and worst case execution time, we can see that there's a difference there between 1.2 million cycles and 2 million cycles. So the worst case execution time here is pessimistic compared to the measurement. So if we look at this function in a bit more detail, we can look at the we can see also that the functions within it have got variability in their execution time too. So we can see that dispatch message has got 3,000 more predicted worst case execution time than its actual measured execution time, and it's executed many times. This is where the idea of a contribution comes in, because although it's a relatively small error from one execution to another, when you consider all of the executions in the test, they aggregate together to make a much larger difference. So let's look into dispatch message. So what we can do, one thing we can do is we can actually look at the source code to see where the variability is. So what we see here is in the source code view, currently we have the high watermark path colored. So this is the longest observed execution time we've seen, and we know that this is being called many times. So clearly what's happening here is through the course of our testing, each of these different test cases, each of these different cases is being executed in a switch statement, which allows us to get a particular execution time. If we look now instead at the worst case path, we see that actually only one of the cases, in the worst case path, what it's assuming is that we're executing many iterations but always going down that one particular test case. So what we might choose to do is to rewrite our test to assume that we always get this case 2 executed, or alternatively we might want to construct constraints which reflect the fact that we wouldn't always receive case 2, and that would allow us to bring down the predicted worst case execution time. So the third tool that we have of interest is Nappy Check. What we have here is a tool which allows us to to monitor constraints. So it's similar to an assertion, but actually it's something that's considered over the execution of a period of time. So what it will do is allow you to establish constraints, which might be timing of specific parts of code. So you might say that this particular function needs to complete within this time. It might be ordering, so this task always needs to happen before that task. Or it might be iteration counts. You might say that we can never receive more than 5 of these messages within this period of time. And then what Nappy Check will do is it will look at the trace which is generated by the instrumented code, and it will automatically identify when the constraints are violated. And then we can work with Rapita and Rapitask to actually see what was going on at a particular point where the constraint did get violated. And so the extension of this to a multicore is, again, conceptually very straightforward. All you need to do is to allow your constraints to be extended to support a multicore environment. In practice, what that means is we need some way of collecting traces that are synchronized in a multicore environment, which is something we were able to do during the Parmarasa project. So we can look at our report again. Just close down these tabs that we're no longer looking at. So we can look at the constraints section, and we can see that what we have is a number of constraints that we've established for many of the different tasks within our system. And we can see that despite the fact that we've run a number of tests, they've all failed on a particular quantity of them. Now I'm going to look into message dispatcher as one particular task of interest. And so we can see there's 4 different constraints that have been set up. 3 of them have got this 97% pass rate, and one of them hasn't been executed at all. So let's actually look into this one here, this runnable 2, having a response time of 4,000 microseconds. So we can look into that. We can see the constraint definition, which is using this special constraint definition language we've established. And we can see the set of failures that have occurred. So one failure occurred during test 10 at this particular timestamp. And the issue was the duration was actually 844,000 microsecond, 844,000 cycles. So it's 8 microseconds rather than 4 microseconds. Again, we can look into the detail of what went on during this test. So because Nappy Check uses a timed finite automata to implement its constraints, we can represent the failure in terms of a particular instance of a timed finite automata. So what we see here is that we enter start state, and then we go to state 2 whenever we see symbol A, which is the start of function runnable 2. So function runnable 2 starts here, function runnable 2 ends, which puts us into this state, which is a goal state. And at the goal state, what we're doing is we're checking the start time versus the end time to see whether or not that's less than 40,000. And what's happened here is that is not true, so it exceeds 40,000, which puts us into an error state. Now you can see that this is a fairly trivial example. It's possible to have much more complex sequences of events, And so there's many possible ways in which a particular constraint could be violated. Anyway, so we see that the timestamp has occurred at 22,727. So we can actually go into Rapitask, and we can see what was happening at that particular point in time. So flip it back to there. So we have a feature in Rapitask that allows us to go to a particular time point. So that was 227272. So that puts that time at the very top of the screen. So we need to just scroll down just a little. And it was affecting Runnable 2. So we can see here, Runnable 2 has got a response time of 8.44 milliseconds, which was the issue we saw. So this is this familiar block of activity, and including this multi-core blocking situation that we see once again. And so we can see that this constraint has been violated, presumably because of this peculiar activity that's been going on here. So I've mentioned during the course of this presentation the Palma-Rasa project. This is a EU research project which has just terminated. It encompasses a number of partners, including universities and technical partners. So Rapita Systems was UK SME partner. We were also working with Honeywell, an aerospace company, Barrel Machining, who make large drilling systems and cranes, and Denso Automotive, a Japanese automotive company with a base in Germany. And the project was looking at parallel execution of hard examples of hard real-time programs running on up to 64 cores. And it was identifying research in order to be able to predict worst-case execution time on multi-cores, which is a hard problem, and looking at ways in which we can get good worst-case execution time analysis with a minimum of pessimism. So if anyone's interested, they can actually look at the details of the project at this website here. That's www.palmarasa.eu. So that's a brief summary of the multi-core activities that we're doing in Rapita, encompassing the main tools that we're developing and how they work on multi-core. So if you have any interest in finding out more about this, or about talking about possibly gaining access to some of these tools through our early access program, please feel free to get in touch through these various means. Alternatively, you might just want to keep up to date with what we're doing. We have a monthly mailing list which is mainly covering technical topics. We don't just put boring marketing stuff on there. I like to think that hopefully something a bit more technically relevant. Likewise, we have a blog which we update fairly frequently with posts on technical topics as well. Okay, so thank you very much, and if there are any questions, I'll be happy to take them now.
Thank you for that, Andrew. We do have a question online, and the question is, what targets do you support?
Well, one of the interesting things about the architecture that we've chosen for our verification tools is that it is target independent. So long as we've got some way of generating code and instrumenting code and putting it onto a target and of getting data off, we can work with that. Having said that, particularly in the world of multi-core systems, we've worked with a number of cores, a number of targets. So, for example, we've worked with the particular hardware that's come out of the Palma-Rasa project, but commercially we've worked with the Freescale P4080. We've also worked with the Oryx processor from Infineon, and for space systems we've worked on the Leon 4 processor, which we've had as a multi-core configuration as well.
That's lovely. We have no other questions online, Andrew. Thank you so much for taking the time to share your tool with us today. I'm sure that if anybody has any questions or would like any further information, they'll contact you. Thank you very much.